Now, Newton's third law leads us to our next real topic, which is free body diagrams. And so really, if you've noticed in physics, we have to draw a lot of different stuff in order to know what's going on. It's very commonplace to be able to have to draw every little thing that's happening in order to figure out what's going on. So let's start with a picture like this. Little baby lifting a barbell. So what's going on? Well, I assume that the baby is lifting and applying a force that's pulling up on the barbell, right? But at the same time, that means the barbell has to be applying an equal and opposite force to the little baby in order to keep it from moving because it doesn't look like it's lifting up. And at that same time, I think that it's also applying a force to the ground because I don't think the baby is able to get it completely off the ground, but it's not falling through the ground. So that one has to be equal. And then you can come back and you can label absolutely all of these. We have, this is the force of ground on bar. This is the force of the bar on the ground. Here's the force of the bar on baby. And of course, the force of baby on bar. All right, so those are some of Newton's pairs, and what we start to do is we're drawing a free body diagram. But this is not a true free body diagram. A free body diagram usually works from a center of mass. So truthfully, I would have written the entire problem like this. I would look at one thing like the baby, and I would say, okay, so that baby is exerting a force on the bar. So baby on bar. And then I would say the bar is exerting a force on the baby. Bar on baby. But then I would also say that gravity is exerting a force on the baby. So force of gravity. I'm just going to do like that. But then also that the ground has to be pushing back up. We call that a normal force because it's what equalizes everything. And we could then draw Newton's pairs from that, but the important thing is that this is a free body diagram. It is a center of mass, which shows us all the forces acting on it. And then we can look at how its motion would change from there based on these things. Okay, so now that we know some about free body diagrams, let's take a look at the types of force acting on a single object. I'm just going to look at some sort of random box, okay? The first type of force that I'm going to refer to is if it's on Earth, gravity is going to be bringing it down. And that's often represented with a capital H and a capital G, but the G is a subscript, and we call that gravitational force. Gravitational force always acts straight down on the center of mass of an object, so the box being pulled straight down. Now, it's going to be balanced out because of Newton's third law. It doesn't fall through the ground, meaning it has a normal force that is applied there. So that normal force is the thing that is Newton's equal and opposite. Now, there's something you need to look at with it. It always works perpendicular to motion. So up here by it, I'm going to draw my little perpendicular sign. Perpendicular. Okay, that's important to remember. Right now, not so much because it's on flat ground, so it's just straight up. But in a second, we'll see why it's a little bit more so. Now, let's say that I had a rope on this and I was applying a force upward, okay? So that force that's applied upward or at an angle is simply called that, an applied force, okay? And that's what we have there with the capital F and subscript capital A. But I said that was a rope, and I said that for a very specific reason. That way I could cover another type of force. In a rope, there is an equal and opposite amount of the force applied going in up to the one end and the other end being applied to that in the rope, and that is called a tension force. And so now we have a tension force there. And so I can apply that there. A tension force is kind of unique because it kind of balances itself out. We can say that it's in the direction, either direction of the rope. It has to have the equal amount in the opposite direction going on, unless the rope snaps, of course. Now, if I'm applying a force here, though, this is going to cause the box to move, right? Newton's first law, an unbalanced force is going to cause motion, right? Even if it was at rest. But that brings us to another force we're going to need, and that would be opposing that motion, and that's going to be friction. Now, I said it's moving, so I'm going to give it a subscript of K. We'll learn a lot more about why when we go over frictional forces. I'll go ahead and do a spoiler. It's kinetic movement, okay? And so that's a good number of forces just to be able to start with and deal with. We need to look at several of these more. Friction is going to get its own video. Force of gravity is going to get its own video. Applied force and tension are pretty self-explanatory, but I need to cover a little bit more of this normal force before we can move on. So let's look at it a little bit more. Now, the reason I want to look at normal force a little bit more is because let's say we had a ramp like this, and then we had a box on said ramp, okay? Now, I could go ahead and put my applied force right here, right? And that's going to be moving it up the ramp. I'm going to have gravity, or friction, that's going to be opposing that motion. We'll say that it's moving. But then it starts to get a little bit more tricky because we then say that gravity is still going to act straight down. Notice that gravity looks like it's at an angle from this because everything's tilted on this axis. That normal force, though, remember it's perpendicular to the surface because it's not keeping it from being affected by gravity, it's just keeping it from going through the ramp. So let's look at this a little bit clearer. So first of all, everything here is aligned with the ramp except for gravity. So if you think about this, it would be much easier to think about it if we could turn the whole thing like that, right? But in real life, you can't turn the world, but you can set up that is the way you want to do things. And so instead of setting up that I want to do it that way, see if I can tilt it back. There we go. I'm just going to say that I'm tilting my axis. So I'm going to draw a key that shows the axes are tilted. It needs to designate which is my X direction and which is my Y direction. And a lot of times you're just going to go ahead and show that that's the positive to the right and up. Technically it should be the same, but we do that just so people know. Now I have a tilted axis that 3 out of my 4 forces are in line with. So what do I do with gravity? I break it down into its vector components. I know, you don't want to break things down, but that's a good part of solving this. Okay? So that means there's a certain amount of that gravity that's pulling straight into the ramp and a certain amount that's pushing down in the same direction as the frictional force. Let's move where I wrote this real quick just so we can write this slightly different. So now I have my force of gravity, and I now have a force of gravity in my X and my force of gravity in my Y. This helps us out tremendously because that normal force, like I said before, is only opposing the amount that's pulling it through. So it's not the full force of gravity. It's just going to be equal to that amount of force in the Y of gravity. Okay? And again, these are not, they're just equal magnitudes. They're not in the same direction. There's a Newton's pair there. Okay? So that's usually how you're going to calculate that normal force. It's going to be equal and opposite of whatever gravity is. Now, if something was being applied down, pushing it down, that normal force would go up. That causes a lot to do with friction, and friction is greatly related to normal force, but we'll see that when we talk about friction. Hope that helps.